welcome you in this session. This session is handed over to you.
Yeah, thank you, Rituj. So, good evening, all. So, yesterday we were discussing about linear transformation. Our starting point was a vector space is defined, and not much is happening in a vector space. So, we start to define function on that. Things which work on the elements of vector space, and then from there the action starts. So we said that we don't want to define any. You can define a function with any properties, but it turns out that one of the interesting class of functions which can be defined on vector spaces is functions which preserve the identity, which preserve the unique thing about these vector spaces, that is their linear combination. That is the function which preserve the linear combination structure, linearity structure. That is, the image of sum is sum of images. That is the way to keep in mind. And then we start exploring it further. And this idea is at very foundation level of mathematics, that we define a set, we analyze what kind of set theoretic structure it has, and then we impose some additional structure on that, algebraic structure in case of vector spaces. Later on, we define some matrix space structure, topological structure. We keep on adding that, and which we make set and these operations, and then we study them. And this becomes we discussed some concepts yesterday. So in order to enrich the algebra, to emphasize wherever possible what kind of algebraic structure is playing the role and what kind of geometrical structure is playing role. Because in a sense, linear algebra, if you see the word itself, linear algebra, linearity is coming from connection with algebra, connection with geometry, whereas algebra is referring to the kind of algebraic operations we do on the elements. So before we go further, can you tell me any two algebraic structure or algebraic property that we studied in yesterday's session? Any two algebraic structures or the algebraic aspects that we studied yesterday?
Yes, addition in vector space and the scalar multiplication.
Yes. Anything else?
Commutativity.
Yes. Commutativity is another algebraic structure that we explored.
W is a ring.
What aspect of ring you are talking here?
So the space of all linear transformation from a vector space V to W.
Yeah, right. And can you also list some geometrical properties that we studied yesterday? Any geometrical aspect that we explored yesterday?
Rotation is not a linear transformation.
Yeah. Rotation is not a linear transformation. Else? Okay. Did we study any properties which combines the geometrical property with the algebraic property? Anything in that direction have we studied yesterday?
Yes, rank space and null space.
Rank space and null space. Yeah. This rank nullity theorem is basically a combination of both the cases. Yeah, where we are trying to combine different aspects together. So today's session will be deeper continuation in the same direction. And whenever you teach linear algebra, you should also emphasize that where the dimensionality is important and where it is not important. It's not true that for all the cases finite dimensionness is important. Let me share application window. Okay. So this is one of the important things that we studied. We define some special spaces related with the linear transformation. And then for a linear transformation, for a finite dimensional vector space, we have this important result that rank of T plus nullity of T is equal to dimension of V. And just to recap, rank of T is nothing but the dimension of range of T. Nullity is nothing but dimension of null space of T. And dimension of V is some finite number. So there are some geometrical concepts or some typical mathematical concepts which also exist there, which we have not touched yesterday. For example, invariance. So invariance means we see whether certain object or a set, how it behaves to certain operation. If it shows some kind of closeness, then we call that it is invariant. So among range of T and null space of T, do you see any invariance property of these spaces? Yeah. The broad concept of invariance is it clear to you? Invariance means suppose you have given a set and certain operation. You take the element and on that, and then see you are still in the same set. You are leaving the set. If you are in the set, then we say that that set is closed with respect to that operation. Take an example of integer and operation as addition. If we add two integers, we are getting again integer. If we multiply two integers, we are again getting integer. But if we divide two integers, we may or may not get an integer. So it means that the set of integers is not closed with respect to division. So do we see any such algebraic property that some space is closed with respect to certain operation or not?
Nullity of T is invariant under T because
Yes. Yes. Yeah. So if I take any element in null space of T and apply T on that, then I'm not going out of that space. But this statement needs to be made precise. It is not a precise because you see null space of T is a subset of V. Whereas when I apply T on that, I'm getting element in W. So n of T is invariant. This is not a very precise statement. Just it requires some small minor repair. What is that?
if the linear transformation is from a same V to V is from the same set, then it
Yeah.
will be.
Yeah.
Yeah.
So others, is this point clear to you?
Yes, sir.
Yeah. So when a linear transformation is from V to V, we use some special word. We call it as linear operator.
Operator.
Yeah. When T is a linear operator from V to V, and then null space of T is basically invariant with respect to that. Okay. So this is interesting. So what is a question we can ask ourselves here? See, living in the age of machines, where machines are getting learning and getting smarter and smarter. So henceforth, our progress depends not only answering questions rightly, but also asking right kind of questions. So knowing the fact that null space of T is invariant for operator T, what is the interesting question we can ask?
Sir, what are the other things that are invariant?
Very good. Yeah. So is it only one space, or there are also some other subspaces which are invariant? Yeah. So, and you will see that when we discuss eigenvalues and eigenvector, there is a connection between of eigenvalues and eigenvectors and these invariant subspaces, right? So later on when we discuss again, we elaborate on this point. So let's quickly convince ourselves that this makes sense. Let T be a linear operator from P4 to P2, given as T acting on P is nothing but second derivative of P. In this case, P4 is span of standard basis 1 x, x square, x cube, x to the power 4. Its dimension is 5. P2, again, we can use standard basis, then dimension is 3. So if we take derivative of all the basis elements, then we see that range of T is nothing but span of these three elements, 2, 6x, 12x square. Yeah? This can be changed, not an issue. And dimension of range, which is basically rank of T, is 3. So according to rank nullity theorem, nullity of T is 2. It means that dimension of null space is 2. So then a question comes, what is the basis of this null space? And in this case, answer can be given by mere operation. Which are living in null space of this operator T.
Sir, x square and x to the power 4?
Is x square in null space of T? So T of x
1 and
square
x.
is 1 and x. Yeah. If we operate T on 1, it is taking us to 0.
It will give 0.
Yeah, if we operate T on x, which is second order derivative, it will take us to 0. So null space is basically span of 1 and x, set of all functions which are linear combination of 1 and x live in the null space of T, and its dimension of 2. So this makes sense perfectly. Yeah. So let us ask ourselves, this rank nullity theorem is also applicable for infinite dimensional space. So suppose V is a infinite dimensional space, then what about this rank of T and nullity of T? Can you think of example how this rank nullity theorem gets interpreted in infinite dimensional space? So if dimension of V is infinite, then either dimension of range or dimension of null space or both can be infinite. Think about the examples where null space is finite dimensional but range is infinite dimensional? Can the other possibility happen that range is finite dimensional but null space is infinite dimensional? So these are the questions which provoke you analyze the underlying structure and interpret the things. So let us look at the matrix version of this rank nullity theorem. Okay? For example, the standard rank nullity theorem says that rank of t plus nullity of t is equal to dimension of V. So when students are learning linear algebra, they are already familiar with the matrix theory. And also in matrix theory, we have notion of rank. Yes, how the rank is defined, how rank of a matrix defined?
The number of non-zero rows in after reducing the matrix in the echelon form.
Okay, number of non-zero rows. Why cannot say number of non-zero columns?
It's the same thing, yeah. Because I'm in echelon form, I'm used to doing the row
Yeah.
operation. That's why I am just saying row here.
Yeah, obviously. Yeah, I'm just poking to think in a different way. So does that mean row rank is same as column rank?
Yes, sir. Always.
Yeah. So it means that rank is some special properties. You can look at the matrix in different ways, but you cannot manipulate the rank. Yeah. So the question comes: is that notion of rank of a matrix, is somehow related with rank of a linear transformation? Now, as a teacher, we know answer. What is the answer? Is rank of a matrix concept related with transformation, or these are two disconnected concepts?
Indicates the number of independent vectors.
It indicates number of independent, linearly independent vectors in which set?
In the range space.
In the range space. Yeah, we have to highlight this thing. Excuse me. So we know that we have seen matrices are one of the special examples of linear transformation. And there, this notion of rank is mapped to column rank or row rank of a matrix. And there also we can show that the column rank of matrix A plus nullity of A is equal to dimension of V. Okay? So it seems that linear transformations and matrices are sharing some interesting underlying properties. And we already know that on a finite dimensional space, your linear operator and matrices, they share very close connection with each other. Okay, so what? For a matrices, we have this kind of relationship. What is the use of this? Okay, so let us explore this question. How can we use this rank nullity theorem with respect to matrices? For example, you have to recall that students are familiar with solving linear system of equation, representing it into row echelon form, and then saying whether solution exists or not. But in that conceptual setting, you need to first reduce the given matrix to its echelon form, and then you have to make the observation. So that is more of a algebraic approach. But if we know the nullity of a matrix, then by using this rank nullity theorem, we can say whether the linear system AX is equal to B is consistent or not. What is mean by system being consistent?
Having a solution.
Okay, having one solution or more than one?
Sir, if one solution exists, then system is consistent. At least one.
Yeah. Yeah. So, for example, suppose I have a system of 20 equations in 22 unknowns. So it's basically A is a mapping from R22 to R20. And suppose the nullity of is 2. And then the question is whether such system will have solution or no. So we have not given the explicit representation of matrix. So I cannot use my theory of reducing the matrix to its echelon form and then doing that. So I have to use some logical argument. And of course, here the basis is rank nullity theorem. For example, let's look at the rank of matrix A. So according to rank nullity theorem, rank of matrix A should be dimension of domain, which is R22. So its dimension is 22 minus nullity of A. Nullity of A is given as 2. So rank of A is 20. So it means that dimension of my range space is 20. And what is the uh, image space here? R20. The only subspace of R20 which has dimension 20 is it itself. So it means that my entire domain R20 is my image set. So it means that for every vector in R20, I can find a linear combination of columns of matrix A. So it means that my linear system is consistent. In this case, I did not deal with the actually reducing the matrix A into its echelon form. But of course, it requires that you need to know the nullity of matrix. Then comes this important concept of matrix representation of a linear transformation. Yeah. So this is a very important concept, especially for those who will be working in signals and system. You will did you have the guest lecture by Dr. Bhatnagar on image processing and signal processing?
Sir, one by Dr. Pankaj Yadav.
Okay, so Bhatnagar sir will talk about signal processing and image processing. So there you will see that this matrix representation of linear transformation plays very important role. Yeah. The reason is that we can store matrices very efficiently on computers and then we can manipulate them. So this is a very important concept. I'm quite sure that you all are familiar with this thing. So I don't want to give too much emphasis on actual derivation, but I want to emphasize on what kind of algebraic structure, geometrical structure, and linear algebra interesting is happening in this setting. So what we do is that we take element V in the domain, and since we know that it has an ordered basis V1, V2, Vn, we represent it as a linear combination. So once, what is the difference between basis and order basis? Very small difference, but
Order is there. Yeah, some numbering we can give to the basis element.
yeah. So far we were talking only about the basis set. It means that you can arrange elements any way you want. It can be V1, V2, Vn, or V2, V1, Vn, or any other combination. But in case of order basis, we fix some order. This fixed order can be anything as per the convenience, but then we stick to that. And once we stick to that, then this, for this linear combination, we don't have to bother ourselves with these basis elements. We can only work with these numbers, yeah? C1, C2, Cn. So the numerical representation of this vector B vector with respect to basis B is set of this ordered set of scalars C1, C2, Cn. So all this argument is basically in the setting of linear algebra, but at the back side, what we are doing is that we are talking about Rn. For example, in case of R3, generally we take I, J, K as unit basis elements in X, Y, Z direction. So we don't say that 2I plus 3J minus 4K. We only say 2, 3 minus 4. And we can locate a point in R3. So it means we are basically detaching ourselves with the underlying basis and just we are representing these numbers. So it's also important that we prefer to have as many as zeros in this numerical representation. It means that there exists some optimal basis. That is where all this signal processing thing starts. So applying t and using its linearity, we get this equation 1. And each of this t of v1 is in basis. So we can represent t of v1 as a linear combination of these elements. Let's call them as a11 w1, a21 w2 till am1 wm. We can do same thing for other elements, and as a result we get this arrangement. Now we can organize this thing in a compact form by using matrix notation. This you have already seen that. So writing this in a matrix form directly, we can write it in slightly different way. This T of V, which is nothing but the coordinates of T of V with respect to B, it's nothing but this linear combination. Now, this is the structure where you are seeing linear algebra coming into the picture. On the right hand side, here you are seeing the coordinates, which is basically a feature of geometry. And whereas on the right hand side, you are seeing the linear combination, which is the algebraic property. And this equation, if you observe carefully, it is showing the interplay between geometry and algebra. Let me pause here for a moment. Think about this statement, that this representation is basically hinting the interplay between geometry and algebra. Do you agree with me?
So because we are using some algebraic properties over vectors.
Yeah. The right hand side is basically algebraic structure, linear combination. Whereas this thing is more of a geometrical representation. This is the representation of T of V in the space W with the basis B dash. Right. So here we are looking it in terms of as a point. Right. It said that it was Descartes who is supposed to be a founder of coordinate geometry. Yeah. He was just lying and looking at the ceiling of his room. He saw that a fly was going from here and there, and he was trying to trace its trajectory. And then he found that at every point in R3, if he gives some coordinates, then and connect these coordinates, it basically gives the trajectory of fly. And then he realized that I can represent every point in R3 as a vector. And if I add this vector, it will also give the trajectories. So there is a relationship between R3 as a geometrical object and R3 as an algebraic structure. And that's what we do in coordinate geometry, right? And linear algebra is basically a finite dimensional generalization of coordinate geometry. That is what happening here. So the same thing in further compact notation is written in terms of matrices. Yeah? And this matrix, we call it as a matrix representation of linear operator T. So from as a matter of convention, we also write with respect to what basis, because if we change basis, this matrix representation will also change. Yeah. So there are mn entries in this matrix representation. Now we can ask ourselves question here that if I want to know linear operator T, I need to know these mn entries. Then I know the action of this linear operator T. So can I have a nice basis representation in which there are many elements in this matrix entry are 0? Yeah. So let me again rephrase this expectation. So action of this linear operator is captured in this matrix, and this matrix has mn entries. So if I want to understand this action of this T, I need to know this mn element, and the nature of this, the exact numerical value of this mn element depends on the choices of basis b, b dash. So can we have a very efficient choice of basis in which many entries in this matrix representation is 0, so that my calculation will be simplified, my storage requirement will be reduced. And this is where Fourier transformation, wavelet transformation comes into the picture. So this is the optimal choice of basis where most of many of these entries are 0. Yeah. So this is also quite similar to the representation of change of basis or transition matrix. So transition matrix means you change the coordinates, then how the matrix representation will change. So students already know these things. We can link with that. So slowly we started with the linear operator, and once we know that underlying space is finite dimensional, then we can actually re-invoke all our understanding of matrix theory to understand this linear operator T. But right now we are doing this in more of algebraic mindset. But slowly you will see that we get into geometrical mindset. So this is a standard theorem which says that every linear operator on a finite dimensional matrix has finite dimensional vector space has a matrix representation. Yeah. So we saw some of these examples. So okay, in this example, you see that I am operating T on the basis. What is the motivation behind this? Why it is enough to operate T on the basis elements?
So
All the
because
other
other
elements will
elements,
be a linear combination of
yes.
basis elements. So
Yes. Yeah. So here we are crucially using the linearity of transformation T. So if it is linear, then it is enough to know the action of T on these basis elements. Then we can recover action on any element by using the linearity concept. So this will be the matrix representation. Okay, looking at this matrix representation, we saw this example a few moments earlier. What was the context of this example? We saw T P4 to P2 defined as second derivative of P. In what context we discussed this example few moments ago?
Rank and nullity.
Yeah. So there we'd argued in an algebraic setting Now look at this matrix representation of T. Whether those arguments make sense when we look at this T.
Yes, sir.
Okay, can you please explain how?
Sir, here rank is 3. Rank of this matrix is 3.
Well, all the rows are non-zero. So 3, okay.
Yes.
And you see that the first 2 column entries are 0.
Yes.
So that is why null space has dimension 2.
2.
Yeah. And this example again confirms that row rank is same as column rank. So this is what we were expecting it. Yeah. So you see that from this matrix representation also we can verify rank nullity theorem. 2 is the nullity of the operator, 3 is the rank, and the dimension of domain is 5. Yeah, so these results make sense. During tutorial also we solved this example. Okay. So now let's come back to the question that we asked. That we saw that when T is an operator, that is T is a linear operator, that is T is a linear transformation from V to V, then we can we know that null space of T is invariant, and we ask the question that are there any other spaces which are invariant? And that question leads to this interesting concept of eigenvalues and eigenfunctions. So let me share those slides with you. Slides visible?
Yes, sir.
Yes, sir.
Okay. So before we get into discussion about eigenvalues and please tell me what do you know about eigenvalues and eigenvector? First, from algebraic point of view. So at this moment, we students are familiar with this concept from matrix theory. So from an algebraic point of view, what do we know about eigenvalues and eigenvectors? Any thoughts on
Hello.
this? Yeah.
A element from the field is called eigenvalue if there exists there is a vector v in the domain v if tv is equals to alpha v. Alpha is that element in field.
Okay. So that is a definition.
Yes.
But, what algebraic algebra related properties of eigenvalues and eigenvectors do we know? Because it's okay, it's Arun is saying that it's a scaling vector. Arun, can you elaborate? That is more of a geometrical intuition. Yeah. The moment you are talking about scaling and this. Yeah. Yeah. Okay. So what is the situation is that we have a finite dimensional vector spaces U and V. We define linear transformation from V to W, and as just now we have seen that such linear transformation on finite dimensional vector spaces has matrix representation. So all the things that we know about matrices, we can now carry over. Then the question comes, what's the new? What is something new what we are doing? Okay. So when students know the notion of eigenvalues and eigenvectors from a matrix theory point of view, what are the things they know? They know the definition of eigenvalue and eigenvectors. They know how to compute eigenvalues, how to find out corresponding eigenvectors. What else they know? Anything else?
Sir, eigenvalue satisfies the characteristic polynomial?
Yeah.
Hamilton theorem.
Yeah. So they also know Kelly-Hamilton theorem. Okay. What else they know?
So product of
Maybe they know.
eigenvalues is the determinant of matrix, and the sum of the eigenvalues is the trace of the matrix.
Yeah. Yeah. And those who studied advanced matrix theory, they also know that there is a relationship between nature of matrices and the nature of eigenvalues. For certain kind of matrices, you get only real eigenvalues. For certain kind of matrices, you get only purely imaginary eigenvalues, so on and so forth. Yeah.
Yes, sir. Yes, sir.
So yeah, so all the thing that they know is basically from algebraic point of view, but we somehow don't highlight on this vector nature of eigenvectors. So this vector is telling that, hey, I'm related with geometry. I'm also telling you something about the underlying geometry or underlying space, but so far it is not invoked. And linear algebra is the place where we are emphasizing on this vector nature of eigenvectors. So if vectors means these vectors belong to some space, if it is a space, then we can think that what is the basis of that space? Is it a finite dimensional space or infinite dimensional space? Is it a vector space? If it is a vector space, uh, what kind of unique thing it has? So our emphasis when we discuss eigenvalues and eigenvectors in the context of linear algebra should be to highlight or to bring forth this vector nature of eigenvectors. And this basically points to the question that just like null space, are there any other spaces which shows this kind of T invariantness? And that concept is closely connected with eigenvectors. Let us look at that concept. Let's first
Sir,
see this.
here one question.
Yeah.
Do we describe do we derive eigenvalues from eigenvector or from eigenvector to eigenvalues?
Okay. Anyone would like to take this question? What is the first thing we do? We go from eigenvalues to eigenvectors or eigenvectors to eigenvalues?
Eigenvalues to eigenvectors.
Sir, we first find a characteristic equation, then we convert lambda into a, then we can directly find AQ.
But we define eigenvector first. From eigenvector, we define eigenvalue.
We have two opposite answers. One answer is that first compute eigenvalues, then compute eigenvectors. So in that case, the approach is first find a characteristics equation and then proceed. So what is the starting point? If we are finding eigenvalues first, then our starting point is From a given matrix, write its characteristics equation. Solve
Sir,
it.
we just use formula a square minus sum of and main diagonal plus
Yes.
determinant of matrix is equal to 0.
Yeah, that works well for 2 cross 2 matrix. But what about n cross n, or even say 3 cross 3?
Is roots of characteristic polynomial.
Yeah. Yeah, there are some comments in. Yeah. So generally, we first find eigenvalues, and from that we find the eigenvectors. Yeah. Anyone knows how to find eigenvectors without finding eigenvalues?
Sir, we can find the invariant one-dimensional spaces for the linear transformation, and so
Yeah.
directly we will get the eigenvectors first.
Okay, so you are actually rephrasing the question. Yeah. Uh, please say it again. This is a very interesting statement.
I think that we can try to find the one-dimensional invariant subspaces of the vector space. Then we'll get the eigenvectors first. Then we can find the eigenvalue corresponding to it.
Okay. I will agree with this statement only if all eigenvectors are distinct.
Yes, sir.
Right?
Yes, sir.
So whether others are following this discussion? Who is this who gave this point of view?
Devanshu Vishwas.
Devanshu. So Devanshu ji is saying that if you find all one-dimensional invariant subspaces of a given vector space, then we can find the eigenvectors. Yes, that can be an approach, but it will work only if all eigenvectors are distinct. Yeah, try to think about this statement. Whether all invariant subspaces, why they should be always of dimension 1. In fact, we will see the example where one such invariant subspace has dimension 2. We will see to this. Let's come back to this question after a few slides. Let's come to this question. Suppose I have this 2 cross 2 matrix A. I want to find A cube. So how do we find it? Simply multiply A 3 times. Any other way of finding A cube from this matrix?
Using daily Hamilton.
Finding characteristic polynomial.
And then we can find. Okay, so who is this answering? Durai? Is
Yes,
Durai
sir.
ji answering this question?
Yes. By,
Okay, Durai ji, then apply the same method to find A to the power 100.
yes.
Is
Yes,
it
we can
possible
get.
to apply?
Yes, which is the linear combination of identity matrix and matrix itself.
Identity matrix and the matrix itself, A to the power 100?
Yes.
How?
We can rearrange it, and when we use we cannot use the division rule here, but as a characteristic polynomial, if you take a lambda power 100, when it divides by the characteristic polynomial, we get the quotient into divisor plus remainder. So the quotient times the divisor is totally 0 by the characteristic polynomial, and the remaining one is the linear combination of identity matrix and A, because it is a 2x2 matrix.
Okay, agreed. It's possible to do that. Any other way of doing this?
Sir, actually, I think first we find a square 8 of 4, then 8 was 5. Then we think the similarity is how we get 8 of 100. Just to guess it, and it is impossible to find 8 to the 100 power exact answer, I think.
So we will see that we can do it in a clever way. Yeah. So again, the same thing. Yeah. So suppose if this A is a diagonal matrix, then can you find A to the power 100?
Easily we can find.
Easy.
Yes, sir.
Easily.
Yes.
Yeah.
Yes,
So
sir.
the problem, the only problem is this nature of this A. If it is a diagonal matrix, we know that how to find it. It's just like finding a number to the power 100. Yeah. So this is where geometry picture comes into the picture. Yeah. So when we look at this A in a right choice of coordinates, then this A will change into a nicer form, and then we can do calculation on that nicer form, and then again come back to the original domain to do this. So this is the another popular trick in the bag of mathematician, that given problem is difficult to solve in the given circumstances. We ask ourselves, where is the difficulty? Under what condition we can solve it? If A is diagonal, I can solve this. So now the motivational question is that, can I reduce matrix A to equivalent diagonal form? Now this word equivalent is very important. Yeah, everything I want to do with A, I want to also get it done with its equivalent representation, and then do it. And this is where we can invoke the geometrical picture and then get that. We'll come back to this question later. Okay. So obviously, we cannot compute A to the power 100 by using matrix multiplication. No, that's not the way to do it. Yeah, there is a better way to do that, and that's what we're going to explore. So first, let us combine this concept of matrices and vectors. Yeah. So A is a linear transformation given by a matrix, and it is acting on a vector. So what is the action of a matrix on a vector? It will give me a vector, right? And in a broader context, vector has a magnitude and direction. And when this matrix acts on this vector, it may change its magnitude and direction. So far we are not equipped to talk about these directions, because that requires the notion of angle, and we have not defined this notion of angle. What is the structure we need to define the notion of angle?
Inner product.
Inner product. And what is the structure we require to define magnitude?
Nor.
No.
Norm. Yeah. So if you want to do better things here, we need a structure of norm and a structure of inner product. And even the nicer thing is that somehow this notion of norm and notion of inner product, they are related with each other. Yeah. Just to cut the long story short, if this norm is coming from the inner product, then we need only one structure. And this is where geometry starts, and we get into linear algebra in a better setting. Yeah. So let us take a special case of it. So what can be a special case of this operation, matrix acting on a vector?
Scalar
Arun,
product. Scalar product.
It change only magnitude, no direction.
yeah, Arun also commented this. So there is some kind of scaling. It is only changing the magnitude, but not the direction. Perhaps direction is only the flipping. That is most boring change of direction. Instead of going up, it is going down. Yeah. So one can always say that I am going up in the negative direction. That is fine. So this is the special case where there is only change in the magnitude, but no change in the direction. And such special vectors, they are called as eigenvector. This eigen is a German word. It means characteristics, something which is very unique. Eigenschaften. It means very personal properties. Yeah, and these are very special vectors, which are called as eigenvectors of that matrix. So now we are going to see that how these matrix, eigenvalue, eigenvectors, they are related with linear transformation on a finite dimensional vector space. So let us interpret these eigenvectors in terms of linear transformation. So in terms of how can we reinterpret this information in terms of linear transformation? Well, these are the vectors which are maintaining their directions when they undergo linear transformation. Yeah, so that is the interpretation in terms of linear transformations, and they are very important. They're basically their origin is in classical mechanics and quantum mechanics. Yesterday, I hinted that in the matrix version of quantum mechanics, we use matrix theory extensively, where eigen and eigenvectors have very important physical significance. Uh, this also comes in connection with solution of a homogeneous linear system of differential equations with constant coefficient. Tomorrow, you will hear a talk on application of linear algebra in differential equation, and there you will get idea that how we are using these eigenvalues and eigenvectors. So now let's see that what kind of linear algebra interaction is happening in the background. So this is the standard definition of eigenvalue and eigenvectors. If A is an n cross n matrix, then we call a number lambda as eigenvalue of A, provided there exists a non-zero vector x such that Ax is equal to lambda x. If x is equal to 0, obviously you can take any lambda you want. So that is the trivial case. So we are interested in non-zero vector.
Non-zero vector.
Yeah, so non-zero vector is the key thing. Then every such non-zero vector is called as eigenvector corresponding to eigenvalue lambda. So if x is the eigenvector of matrix A corresponding to value lambda, then so is any constant multiple of that. It means that these eigenvectors are unique up to a multiplicative scalar. And you can choose this scalar as per your convenience. Mostly in physics, some kind of normalization is used to decide the nature of this C. The proof is very easy, where we are using this notion of linearity. Okay, so here is the question. Uh, you can define the notion of eigenvalue and eigenvector. Can we define this notion of eigenvalue and eigenvector for a non-linear operator?
No, sir.
No.
Can we define or no?
No, sir.
Why? Why we cannot define?
Because we want a scaling also, na magnitude. So if we are defining this concept for non-linear transformation, then they will change the direction as well as magnitude also.
Yeah. Yeah. So you can define the equation Ax lambda x, but then if you change the scaling of x, then the result may change drastically. So in case of non-linear things can change unexpectedly. If you change your x by c times x, where c is even c, if you take c is equal to 0.9999. Yeah? So in case of non-linear, things are pretty different. So this thing holds true only for structures. And this is what students generally know, how to find eigenvalues and eigenvector. So it starts with basic definition, Ax is equal to lambda x. If this is true, it means Ax minus
Determinant
lambda
A
x is
minus
equal to
lambda
0.
x. 0.
Yeah. So then we basically define a new operator, A minus lambda I acting on x is equal to 0. Okay. So in terms of vector space operations, how can I interpret this equation? A minus lambda
If
I.
means determinant A minus lambda is singular.
No,
Matrix A minus lambda is singular.
no, that is not the interpretation in terms of linear algebra.
Homogeneous equation.
Homogeneous equation.
No. If x is an eigenvector, if
Sir,
I
this x is
apply,
the null space, and this x belongs to the null space of the operator A minus lambda.
minus lambda.
X
yes,
is non-zero vector.
very good. Yeah, yeah. This is the non-zero vector in the null space of this operator A minus lambda I. Yeah. So now we can look at this thing in a better way. Okay. So obviously, when x is equal to 0, this holds true. I'm interested in non-trivial solution. And then this is generally what happens in matrix version. This equation will have non-trivial solution when determinant of A minus lambda I is equal to 0, right?
Yes, sir.
Yeah, this is what we do it. And this determinant of A minus lambda I is equal to 0 is called as characteristics equation of matrix. And whereas there is related characteristics polynomial for a matrix A. So generally this is what students know. Okay. Now to enrich the learning, now we need to say that you can translate all this knowledge that you have about matrices for a linear operator. And why is this possible?
So every linear operator can be associated. Yes.
Every linear
associated
operator
by matrix can
on
be
a finite
associated by a
dimensional,
matrix. Yeah.
yeah, on a finite dimensional space. Yeah, yeah. So that is what is more or less the broad idea of going further. And then there is this Cayley-Hamilton theorem. From Cayley-Hamilton theorem, linear algebra opens a new detour. You can go more and more in the direction of algebra. You can define the ideals, you define the minimal polynomial. Yeah. So one way goes from here. So this interpretation is useful for MSc students. Yeah. But generally for matrices, what we say that every square matrix, they generally don't talk about the field, satisfies its own characteristics equation. So it means we have a characteristics polynomial like this. Instead of lambda, if I put a, I get characteristics polynomial of a. And this Cayley-Hamilton theorem says that if a is a square matrix, then p of a is equal to 0. Hey, but we are not studying matrix algebra. We are studying linear algebra. So what is the connection of this with linear operators? Yeah. So the connection with linear operators on a finite dimensional vector space is that such linear operator has a matrix representation. So essentially, we can invoke all of these things. And what are the applications of this thing? You know that by using Cayley-Hamilton theorem, we can compute the A inverse. So we can use that knowledge to say that by using Cayley-Hamilton theorem, now I can also find T inverse, right?
Yes, sir.
Because if I know A inverse, I know the matrix representation of T inverse. We can use it to compute the higher powers of A, that is T to the power n. Of course, this is more of theoretical interest. There is a better way of finding higher powers of A. We will see it. So all these things student know, and the first new thing they study is defining this Eigen space. The moment we have these vectors, let us collect all the vectors, eigenvectors corresponding to eigenvalue lambda. So let us collect all x belong to Fn. F can be R or C, such that Ax is equal to lambda x. So span of these vectors is called as eigenspace of matrix A corresponding to eigenvalue lambda. Now again the story is repeating. From some mathematical operation, we get hold of some interesting vectors, and then we are collecting all these vectors, which gives us some set. Now, what are the interesting questions we can ask about this this set? Recall all the understanding of vector spaces. The moment you see this set,
Sum of two vectors. So sum of two eigenvectors is again eigenvector or not?
yes.
Then
And what is the related question to sum?
Sir, scalar multiplication.
Scalar
If you
multiplication.
multiply eigenvector by a scalar, then
Yeah.
what is the
So
case?
We can associate.
how can we combine both of this property and ask just one question rather than
subspace?
asking? Say it again.
Is it subspace?
Are they satisfy linearity property? Yeah, it's a subspace.
Linear combination of two eigenvectors is again eigenvector.
Yeah. We can make this question even interesting. This is definitely delicious, but we can make it even spicy. How? We can ask, is there some vector space structure involved in eigenspace? You see, this question is better than the earlier question.
Yes, sir, it involves all those questions.
Yeah, because all those questions are automatically invoked here.
Yes.
Yeah? So this is very important that we need to train the minds to see the similarities or try to explore the patterns in some of the standard structures that we have studied and the structure under consideration. Yeah. And that requires asking very precise questions. Yeah. And it's always the iterative fashion. It's not that in the first instance itself we ask a precise question, but as we go further, we can make it more and more interesting. So we are asking ourselves the question here, whether this eigenspace has vector space structure. We'll explore that. Yeah. So one thing is sure, that this V lambda is the collection of set of eigenvectors corresponding to A. But if I want to explore vector space structure to it, something I need to ensure that something is also there. What is that something?
Zero.
Yes. Yeah. I'm not bothered about defining the operations because these operations are directly coming from underlying space. But what we need to ensure that is there a zero vector? Yeah. Obviously, zero vector is not the eigenvector. We need to explicitly include it that there is also this zero vector. Yeah. And the claim is that this V lambda, it's a subspace of Fn. But we can also look at this question in slightly different way, that V lambda is the null space of matrix A minus lambda I. So my claim is that both of these statements are equivalent to each other. Am I right?
Yes, sir.
Yeah. But the second question is very interesting because in the second question, we are working at the higher intellectual level. Yeah. We are appreciating that V lambda, elements of V lambda are coming from the null space of certain matrix operation. Yeah. And we know that null space of a linear transformation is a subspace. So when we look at question 1, claim 1, from the point of view of claim 2, then it shows that the mind is looking at the question in a different point of view. And I don't have to give any proof for this statement because I'm using the statement that null space of a linear transformation is a subspace, right? So in the first thing, you need to show that linear combination of elements of V lambda also belongs to V lambda. There is also zero element. Yeah, lot of groundwork is involved in that. Whereas in the second case, I'm using the logical statement saying that I know that for a linear transformation, null space is a subspace. V lambda is a null space of this A minus lambda I, which is a linear transformation, hence proof. Yeah. So in the first case, the proof is algebraic, whereas in the second case, it is in the framework of linear algebra. Right?
Yes, sir.
Here we are only bothered on focused more on V lambda, but here we are also knowing that we know the origin of elements of V lambda. So it's important that we should able to look at the same thing from a different perspective. One may be better than other. Yeah. Okay, the proof is very simple. Go with the definition of V lambda. It's just rearranging this condition Ax is equal to lambda x as A minus lambda I acting on x is equal to 0. And if you write this statement in words, then you get that V lambda is the null space of matrix A minus lambda I. Okay, so now we get hold of vector space. Then what are the interesting questions we can ask about this vector space? Again, it's the same story repeating. What is the thing that is on my mind?
So what is the dimension of this vector space?
Very good. We can ask ourselves, what is the dimension of this vector space? And
Basis.
what is
What
the
is
next?
the basis?
What will be the basis? That will be the next thing. Okay. Before we take this, let's look at this example. Very simple example. We need to find eigenvalues and eigenvector of A. Most of the students will do it. It starts with the equation Ax is equal to lambda x. You set up it. You get this homogeneous system of equation 1. Then for non-trivial solution, we need characters. We find the roots of characteristics equation, which gives this determinant. On solving it, we get the eigenvalues. Most of the students will able to do this, and then we take a one of the eigenvalues, and from that we are finding the eigenvector. Put this value of lambda in equation 1, you get this equation, and you get the solution in terms of parametric solution in terms of one parameter. Yeah, and recall the statement that if x is the eigenvector, c times x is also the eigenvector. So we can simply take, without loss of generality, t is equal to 1. So corresponding to lambda is equal to -1, we have this eigenvector. Yeah. I'm quite sure that you all know how to do this. Same thing we'll do with the second eigenvalue. Lambda is equal to -6. We get another thing. The first eigenvector is column matrix 1, 2. Second is -2, 1. Okay. So far straightforward, right? Nothing new. Let's come to this example. Find the eigenvalues and eigenvectors of this matrix. Can I find eigenvalues of this matrix without doing any computation?
Yes, sir.
Yes, so there are diagonal entries in this matrix.
Yeah, it's a upper triangular matrix, not a diagonal, upper triangular. And the diagonal entries are the eigenvalues. So I know what to expect. And if you follow the procedure followed in the example 1, you will get this kind of eigenvectors. Okay. So far things are getting a little bit boring. Follow the procedure, you get eigenvalues, eigenvectors. So what? This is what all the students know so far. But now we will change the course of action and do something different. Yeah. So let me create a diagonal matrix D whose diagonal entries consist of these eigenvalues 3, 4, 1, and corresponding to, for example, in this case, D11 is 3. So I will write the corresponding eigenvector in the first column of this matrix P. Corresponding to eigenvalue 4, I write the eigenvector in the second column, and corresponding to eigenvalue 1, I write the eigenvector in the third column. I can start with anything. I can also write here 1, 3, 4. And eigenvector corresponding to 1 will be the first column. Only that is the thing we need to do it. Okay. So why are we doing this? Well, there is a reason for that. Now check that if I multiply A into P, this is same as P into D. Or in the other way, A is equal to P D P inverse. And this is a very important concept for our subsequent discussion. So we call A, this is called as, this matrix D is called as a diagonalization of A. Yeah. You recall the first question I asked, that given a matrix A, I need to compute 100 power of that. It's very dirty work to do that. But if A would have been diagonal matrix, I can do it very easily. Yeah. So for this diagonal matrix, if I want to compute any power of this diagonal matrix, it is nothing but that power of diagonal entries. Very easy to do it. Yeah. But why it should be related with the certain power of matrix A? Now that is a very interesting question. Let us take up that question. So that brings us to the concept of similarity of matrices or similarity transformations. So if if A and B are n cross n matrices, then we call the matrices are A is similar to B if there exists invertible matrix P such that A is equal to PB P inverse. Yeah. This P is an invertible matrix, and these two matrices are related with each other in this sense. Then we call them as similar matrices. And when this B is specifically a diagonal matrix, then we call A is diagonalizable. And this is very important concept, especially later on when you study solving nonlinear system of differential equation. This is one of the interesting topic of mathematical research in the field of dynamical systems. Dynamical system basically study of solution of nonlinear differential equations, system of differential equations, which leads to interesting phenomena like chaos and fractals. So there it is very important to understand the structure of these matrices. Hopefully in tomorrow's session, you will get some idea about that. Yeah. And this diagonalization is basically carried out by using eigenvalues and eigenvector. But if you see the procedure, the way we introduce it, it's more of algebraic nature. What is happening geometrically? Yeah. So that is a very interesting question. Geometrically, basically, what is happening is that we are doing a kind of change of coordinates. Yeah. Matrix A, we are changing coordinates in such a way that it has a nice diagonal representation. And what is the choice of coordinates? It is given by these eigenvectors. So if I have set of vectors, it is natural to ask the question, can this set of vectors be a basis for a certain space? If that is the case, what is special thing about that space? All those questions we can ask. So let us look at this example. Suppose this is a matrix A, and we want to find its eigenvalues and eigenvector. By following the same procedure, we get this characteristics equation. In this case, lambda is equal to -3 is repeating 2 times. So we call this eigenvalue lambda is equal to -3 has algebraic multiplicity 2. Yeah, algebraic multiplicity is nothing but number of times this root is appearing as a part of characteristics equation. And corresponding to this lambda, we have two eigenvectors, -2, 1, 0 and 3, 1, 0. And if I define the eigenspace corresponding to lambda is equal to -3, set of all linear combination of these two vectors. The first question, are two vectors independent?
They are independent vectors.
Yes, sir. And different.
Yes, they are.
Okay, why? What is the geometrical answer for this?
They are different plane. They are in different plane.
Yes, that is the
second one is axis plane.
Yeah, that is the geometrical point of view. And what is the algebraic point of view?
They are not a multiple of others. One is not a multiple of others.
Yeah. Yeah. So if you take the algebraic, if you take the, if you take the algebraic point of view of linear combination, then it involves some calculation. Then only you come to conclusion. But if you take the geometrical point of view, it's very intuitive. One vector is in xy plane, other vector in xz plane. You cannot express one by using other. You cannot get something out of nothing. Yeah. So you see that depending on our position of advantage, we can use either one viewpoint over other. And you see that both of these vectors are linearly independent. So the moment we talk about linear independence, it means they are acting as a basis for this v lambda -3, right? And what is the dimension of this vector space?
2.
It will be 2.
2.
Yeah, and this 2 is called as geometrical multiplicity of these eigenvalues. Now, again, you see very nice interpretation between algebraic point of view and geometric point of view. Corresponding to eigenvalue lambda is equal to 3. Once we are saying that it has algebraic multiplicity 2, when we are looking it as a part of characteristics equation. equation which is coming from algebra. And when we look at the space and its dimension, then we are saying it has geometric multiplicity of 2. It's not necessary that algebraic multiplicity is always equal to geometric multiplicity. They can be different. Yeah. And when algebraic multiplicity is equal to geometric multiplicity, it leads to modification of notion of eigenvectors. Anyone knows what is this new version of eigenvectors? When
Jordan
algebraic
canonical forms.
Not exactly. It is going in that direction, but we cannot find eigenvectors. But we
Generalized eigenvector, I think.
Yes, you are right. Yeah, it leads to a new concept of generalized eigenvector. And by using this generalized eigenvector, as one of you rightly pointed out, this Jordan canonical form, that is very, very important concept which is coming up when we go from here. So far, whatever we are doing it's more on the familiar ground, but Jordan canonical form is the important thing, and it has a lot of important applications in the theory of dynamical systems. If you have some system, whether your system will stabilize around the equilibrium point, or it will what kind of behavior it has around equilibrium point, all those questions are intimately connected with the Jordan canonical form of a given system. Yeah. So this basically gives us definition of algebraic multiplicity and geometrical multiplicity. Algebraic multiplicity of eigenvalue is nothing but the multiplicity of corresponding root of the characteristics equation. This property is related with the algebraic structure. And geometric multiplicity is the property related with the geometrical structure. Yeah? And when I'm saying geometry, I'm talking in a generalized sense. So here you see that in linear algebra, both the geometry and algebra, they are interacting with each other. I guess my time is about to finish. So before I finish, let me talk about something that I kept incomplete, how to compute these higher powers of x. Yeah. When this A is n cross n matrix, and we can find a similarity matrix, which is a diagonal matrix, then we can do something interesting. Yeah. If A and B are similar matrices, then they have the same eigenvalues. Yeah. So this is a very interesting property of systems. It means that if you do proper change of coordinates for a linear transformation, then you are not affecting its eigenvalues. Yeah. So it's easy to prove this statement. Just start with the definition of similarity matrix, and then you can prove it. So what is the interesting question we can ask if we accept this theorem? The theorem saying that they have the same eigenvalues. What is the interesting question we can ask?
The eigenvector corresponding to these eigenvalues.
Oh, see,
Will they have the same eigenvectors?
Yeah.
Will they have the same characteristic polynomial?
Yes. And what is your expectation?
The characteristic polynomial is same for the similar matrices. And eigenvectors are different. May or may not be different, yeah.
May, in fact, we will see that they won't be same. Yeah.
Yes.
If you do some calculation, you will see that matrix P is doing some changes in that.
Yes.
Yeah. But since they have the same eigenvalues, the characteristic polynomial is not changing. But when it comes to the space is different. Yeah. So this shows that even though they both are talking about the same thing, if you make some changes, the changes can happen only in one aspect, in the geometrical aspect, but not in the algebraic aspect. And this is very interesting. Sometimes if you make some changes, then it affects only part of it, but not the other part, which can be explored further. So, but why are we interested in diagonalization or a diagonalization of a matrices? Yeah, it's because if we can diagonalize the matrix, and a to the power k is nothing but p d to the power k into p inverse. And since d is a diagonal matrix, we can compute any power of it very easily. So in that way, at the starting, when I ask you the question, can you compute a to the power 100? If you can diagonalize it, then you can easily find out. So that asks us the question, can we always diagonalize a given matrix? Yeah. So fine, it's very important to diagonalize it, but can we always diagonalize it? So before I stop, I just want to give this result that, well, it's not possible to diagonalize matrix always, but if it has n linearly independent eigenvectors, then we can diagonalize it. Yeah. So how can I interpret this statement that matrix A has n linearly independent eigenvectors in terms of a linear operator and vector spaces? Now this is a quiz for all of you. Suppose T is a linear operator from V to V, and A is the matrix representation of T. If A is diagonalizable, it means there are n linearly independent eigenvectors. Then how can you put all these things together and make a statement for a vector space?
T has a basis exactly containing n elements. That means dimension should be.
Very good. Yeah. So that is the thing. In fact, in this case, these eigenvectors acts as a basis, and these are the best basis that you can expect for that linear operator. Yeah. And best in what sense? That you will study when you start talking about the optimization problem. Yeah. So, and it is crucially used in application in solving system of differential equation that you will study in other sessions. Okay, so that's what I wanted to share with all. I hope that I gave you enough cases to think that how in linear algebra we can enrich the experience by taking the algebraic point of view, geometrical point of view, and interaction between them. Yeah, I try to experiment with this, and if you get any new ideas, any challenges, do share with me. I will happy to hear from you. Stay in touch. Enjoy doing mathematics. Thank you.
Thank you very much,
Thank you,
Dr. Kiran.
sir.
Thank you, sir.
So I would like to
Thank you, sir.
inform you that this in schedule, actually these lectures were given to Dr. Sukhendu Ghosh, but due to some unforeseen circumstances, he could not deliver these lectures. So I requested Dr. Kiran at the last moment, and he kindly agreed to deliver these lectures. And he obviously, as you know, had delivered the wonderful talks. Thank you very much, Dr. Kiran.
Thank you. I hope I did some justice.
Yeah. These are very interesting talks. So,
Ma'am, one question.
yes, please.
Ma'am, is it possible to share this presentation?
Dr. Kiran.
Yeah, I can share these things with you, Dilpreet, and then you can share it with all the participants.
Vijay, I will forward you all this material as soon as I get from Dr. Kiran.
Okay, thank you, sir.
Ma'am, please share it.
Sure. Okay. So anyone has any question for Dr. Kiran, because this is last lecture? But he will be joining us for tutorials throughout this program.
Yeah.
So thank you very much, Kiranji.
Thank you, Dilpreet. Thank you all. Have a good time.
So
Bye-bye.
I would like to announce that tomorrow, Dr. Sukhendu Ghosh will deliver lecture on applications of linear algebra in differential equations. So tomorrow we have 2 lectures of 1 hour each with 15-minute break in between. So first lecture is at 5 p.m. to 6 p.m. The second one is from 6:15 to 7:15. So I have already sent meeting link to all of you. So please do join tomorrow for learning applications of linear algebra in differential equations. Thank you, everyone. Bye.
Thank you, ma'am.
I'm going to end this meeting. Bye.